This is TWIS. This Week in Science, episode number 1073, recorded on Wednesday, August 26, 2026. What's up with weather in the West? Hey, everyone, I'm Dr. Kiki, and tonight we will fill your head with weather, climate, and maybe some brains, because, you know, I like baby brains and other brains and all sorts of brains. But first, thanks to our amazing Patreon sponsors for their generous support of TWIS. You can become a part of the Patreon community at patreon.com/thisweekinscience. Disclaimer, disclaimer, disclaimer. When I leave this mortal coil, I hope it is said that I gave instead of took, that I taught instead of told, that I shared instead of stole, that I laughed and loved and inspired the same in others. The world is a little less today with the passing of Dolly and Tim, but I hope you prefer, as I do, to think of the richness that they brought to the world while they were in it. We are all better because of their kindness, determination, and spirit. Let's all do the time warp, because we're working 9 to 5 again on tonight's episode of This Week in Science. Coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening, what's happening, what's happening this week in science. What's happening, what's happening, what's happening this week in science.
Good science, everyone. Welcome to another episode of This Week in Science. I'm back again. No Blair tonight. Justin's still not here, but I am joined by the amazing Dr. Daniel Swain, and we are going to have a great conversation about weather, climate, specifically El Niños. I also have stories tonight related to the shingles vaccine, maybe some bad antibodies for science, a pulsating mass that isn't quite right for you yet, and baby brains. But before we jump into the show, I do want to remind everyone that if you are interested in listening to This Week in Science, we are live on Facebook, YouTube, and Twitch on every Wednesday night, 8 p.m. Pacific time-ish. And you can find those recordings on those networks, on those platforms. After the fact, we also podcast. You can find us. Look for This Week in Science on favorite podcast platform. Our website is TWIS.org, TWIS.org. Go there if you're interested in show notes, information about our stories, our guests, etc. We also have a link to our Patreon and also to our Zazzle store there. Please help us grow. Get other people to subscribe. And it's time for the science. Thank you, everyone, for joining me tonight. And I am going to take this opportunity to introduce our guest for the evening, Dr. Daniel Swain. Daniel is a weather and climate scientist focused on the dynamics and impacts of extreme events. These are droughts, floods, storms, wildfires on a warming planet, which not just a warming planet, I would say our warming planet.
This one.
This one. Daniel's primary appointment is as a climate scientist, associate researcher at the California Institute for Water Resources within the University of California, Agriculture and Natural Resources, and has also been a research partner at the NSF, National Center for Atmospheric Research. I feel a connection, even though we haven't met in person, as a fellow UC Davis alum. Daniel also got his PhD at Stanford University in Earth System Science, and his postdoc work was at UCLA. He authors the Weather West blog at weatherwest.com, and is also on Blue Sky and YouTube at Weather West. Welcome to the show, Daniel. Thank you so much for joining me.
Thanks for having me. I'm glad we were able to squeeze this in between all of the geophysical excitement these days.
Yeah, this hot northern hemisphere summer in the West Coast, we've got fires, there was a massive, they call it a flash flood, but it was a glacial event apparently in Nepal. We've got extra hot in Southern California. We've got the El Nino. And is there more? Am I missing more?
Well, that's a pretty good list of today's events, I guess.
Okay.
But there's just been such a laundry list of things going on recently between the record-shattering heat events in Europe and North America and South Asia and extreme precipitation. The list goes on, which is kind of the point. You can pick any month these days and find a lot of unprecedented extreme heat events, not finding too many unprecedented extreme cold events these days.
Yeah, so that is one of the interesting things, right, with the way that the increasing temperatures are shifting. And people talk about in the summers, you have hotter nights so that there isn't as much cooling at night, and in the winters you maybe don't have the extreme cold as much. Is that generally the trend?
Yeah, I mean,
is it north and south everywhere?
Obviously, it depends a little bit, where you are and the season, but we often think about climate change as sort of shifting the whole temperature statistical distribution upward toward warmer temperatures, and then sort of keeping some symmetric distribution. And that's actually not always what happens. We have seen in the US and a lot of the world that the nights have warmed faster than the days on average, which has resulted in some people maybe underappreciating just how much warming there's been, because a fair bit of it has been at night when we're a little bit less active. Hopefully, not everybody, but for a lot of people. And we also think about the average temperature change and not as much about the extremes. But in many cases, it's the statistical tails of the distribution, the hottest hots and the coldest colds that are shifting most dramatically. And that's actually sort of where we really feel a lot of the impacts. To your point, we're losing a lot of that really extreme winter cold, and we're gaining new magnitudes of extreme heat on the upper end. In some places that's happening faster than others, but the summer's been a real poster child for those extreme heat events in Europe and North America in particular.
Yeah. So you were at UC Davis around 2011, is that? Or you were
I got to think
2010?
About it. Yeah, I think ending in 2000 and early 2011 was when I was not there on a permanent basis. All I will add, I'm in Davis more often than a lot of places these days.
That's interesting. Well, I grew up in the Central Valley, went to UC Davis, and there's the long time period of human experience, right, where we grow up in certain places and the weather is a certain way. It was always hot in the summer in the Central Valley. That's just an expected regular occurrence. But now it's much hotter. It's for longer periods of time. And I remember growing up, we talked about, and when I was doing TWIS years ago on KDVS at the radio station in Davis, we would talk about El Nino's coming, and we would talk about the weather or the climactic changes that were occurring. And I feel like El Nino's happening more often than it used to. Is it happening more often, or are people just talking about it more?
So this is always sort of a perennial question when it comes to extremes in a warming world, is how much of this is smartphone camera era. We're documenting everything, and so we're seeing more of everything, as opposed to how much of things are truly changing. And often it ends up being a mix of both things, where things actually are increasing, and also we hear more about them by virtue of the interconnected world that we live in. I think El Nino is an interesting one because very few people, if any people, are actually documenting El Nino per se. They're documenting maybe the indirect effects of El Nino, but I guess maybe this first makes sense to back up and ask, what is El Nino?
That was going to be one of my next questions. Absolutely.
So I'll back up and answer that one first, and then come back to the question about how it's changing. And I think this one's, in a trivial sense, is kind of a straightforward answer. What is El Nino? El Nino is an episodic warming of the eastern equatorial Pacific Ocean. That's it. That's what El Nino is. It is a warm blob of water on the surface of the ocean in the eastern part of the tropical Pacific Ocean. So think near the
close to the
Galapagos Islands.
west coast of the northern and southern hemispheres of Americas.
Yes. So under
on the
normal circumstances, the eastern part of the tropical Pacific, so we're talking the Pacific off of the coast of Peru and Ecuador near the Galapagos Islands, is actually pretty cold for a tropical ocean. It is not as warm as you would expect. It's certainly not as warm as the Western Pacific. So think Indonesia, for example, where the ocean is sometimes almost bathtub warm. It's not quite as chilly as the ocean off the California coast, but it is much colder than you'd expect for a tropical ocean. And the coastal climates in Peru, for example, mirror that. They're much cooler and cloudier than you might imagine. There's a lot of marine layer and fog there, kind of like San Francisco, but on the equator.
Yeah.
But what happens during El Nino is that actually dramatically reverses. And it's as if, the ocean off the coast of San Francisco were suddenly 10, 15 degrees warmer. That's actually what's happening off the coast of Peru right now. And unlike a terrestrial heat wave, where it's not unusual during, a Central Valley heat wave in August to have temperatures 10 or 15 degrees above average, that wouldn't be all that extreme. It would be very extreme if the ocean were to warm by that same amount, because of course, as we know, it takes a whole lot more energy to heat up water than it does to heat up air. And so this is a vast shift of energy from the West Pacific to the East Pacific. That warm water literally sloshes eastward over the course of weeks and months. And it gets
so the hotter water is coming from the Western Pacific and just is it through gravity waves, the surface waves that kind of carry it, or is this oceanic currents that are pushing the water? So
there's actually two things that are happening. One of them is primarily gravity, because it turns out that the Pacific Ocean is actually sloped. The surface of the Pacific Ocean is higher by about 2 feet in the West Pacific than it is in the East Pacific. So it's not something that's perceptible, but the persistent east to west winds keep the ocean sloped. And I'm exaggerating, of course, because
but making an example of it.
The entire slope over the course of several thousand miles is probably literally not that much more than my arm. But, it's the whole ocean is sloped like this under normal circumstances, because the winds are pushing. So there's this winds holding up the water slightly higher in the west. Gravity wants to equilibrate it, make it even, but the winds are providing the force to keep it from sloshing back due to gravity.
That's so interesting. Okay.
And then we lose those winds. So by whatever means, and sometimes it's random. Sometimes it's just, there's a big storm north of the equator and it causes the easterly winds to become westerly just for a few days or a week. But sometimes that's all it takes. You get one or two of those events in a year, and that water starts on the move because gravity really wants to make it slosh back eastward. And so the water is much warmer. So when it does move east, it's transporting warmer water in toward the east. But then the other thing that happens is that once you no longer have those strong easterly winds blowing, the other thing that happens is that the eastern side of the basin, so again, near Peru, near the Galapagos Islands, normally you'd have those east to west winds inducing upwelling, so vertical movement of cold water from the deep ocean, because the surface water is getting pushed westward.
So you're kind of making the circulation occur because of the force.
Because the water can't materialize out of thin air, it can't come from east to west from the continent because it's a continent. There's no water. It's got to come from somewhere, unless it's going to create a massive vacuum in the East Pacific Ocean. And since that's not going to happen, it comes up from beneath. And so you have cold, nutrient-rich water. So this is the normal state of things. But during El Nino, you already have this warm water on the move, sloshing eastward. And then you lose this cold water upwelling as well at the same time. So it's a secondary mechanism. It's not warming, but it's lack of cooling.
The cool water, the cooling water is not coming in to compensate.
And so the combined result of that is actually pretty dramatic. The net effect is that the surface gets a lot warmer, and this process becomes self-sustaining after a certain point, because once you start to get warmer water, now those easterly winds don't want to blow as much. And so as soon as you establish this process, it's a vicious cycle, positive feedback, where once the initial warming begins, additional warming wants to occur by virtue of the initial warming, which begets even stronger warming. That's where we are now with this this positive. So anyway, so that's
this is a normal cycle. This happens where you have the movement of the air against, by the winds. You have the loss of that. You have the warming of the eastern part of the Pacific. This is what the El Nino Southern Oscillation. And
yes, this is
right?
all a natural process.
Yeah.
The El Nino is the warm phase of this semi-cyclical process. La Nina, the cool phase, would be the other end of the spectrum. And this is one of the very few things we often talk about climate cycles, and I'm using air quotes in case anybody's just listening to the audio, because they're not. Most of the things we talk about in the climate are not really cyclical. They're just things that happen occasionally, but kind of randomly in time. But El Nino and ENSO, El Nino Southern Oscillation, they're an exception to this. They actually are semi-periodic. We go back and forth every 2 to 7 years or so. And the reason for this is essentially El Nino is serving as a giant global thermostat or an emergency heat release for the climate system. So over several years, a lot of excess energy accumulates in the tropical oceans. You constantly have that hot tropical sun beating down on them. You have ocean currents that allow water heat to accumulate in that ocean, and it's got to, unless it's just going to continue warming up without bound, it's got to go somewhere and equilibrate. And the way that happens is through El Nino events, which then end up releasing vast amounts of energy stored in the deep ocean into the atmosphere in the eastern tropical Pacific when it warms through evaporation and heat transfer. And that is why El Nino matters so much for the rest of the world. Obviously, it matters if you're in Peru or Ecuador or the Galapagos Islands because it's locally a dramatic effect. But all of these indirect effects in Indonesia and Africa and California and everywhere else, they arise indirectly from this enormous heat release that's occurring in a part of the tropics where it doesn't usually. And so this alters global weather patterns and storm tracks and increases the total amount of moisture and energy in the global atmosphere at large. And so it ends up being, especially if you've got a strong event, as we do this year, we'll talk more about that.
Yeah, that's what we want to talk about.
A big deal.
Yeah. So this energy release, so the kind of buildup of energy and the storage of energy, like we know that the ocean has a high heat capacity. And so as we're talking about climate change and people talk about that wonderful blanket of greenhouse gases in the atmosphere that's leading to the trapping of heat and the eventual transfer and storage of that heat in the oceans. How is this related to this cycle of El Nino, La Nina?
So, as I've alluded to recently, we live essentially on a water planet. Something like 70% of the Earth's surface is covered by water of some form or another. It's mostly oceans with some small contribution by giant lakes and such. But it's a water planet. If you were to just use one descriptor of what most of the surface of the Earth is, it's a liquid water. And that matters because, the Earth system is warming, and we call it climate change. We call it, but global warming actually encompasses not just climate change, but also ocean change. And in a lot of ways, it is actually primarily ocean change because that is where the majority of the accumulated energy is going as the Earth system warms. Now, the challenge is then that the ocean is tightly connected with the atmosphere. And so what goes into the oceans does eventually come out in large part back into the atmosphere. And in fact, much of that occurs during El Nino events. That is the mechanism that the Earth system uses to, for lack of a better term, burp out all this extra energy in these.
And so, and when you're talking about it coming out and the energy transfer, we're getting a lot of evaporation, water vapor, and this is when we talk about in California or on the west coast of the Americas, we talk about El Nino, we expect precipitation. This is part of it, and the warmth of the precipitation also is a factor in getting the heat and the water out of the ocean.
So what's interesting is that the main way that the ocean actually gets the energy out is through latent heat release. So it is directly through evaporation of huge amounts of water from the surface of the ocean where it is most anomalously warm, and we know, that the amount of energy that's required to evaporate water is very high. And so what's happening is that there's this enormous evaporation event occurring over this really warm water. That's actually way more efficient at transferring energy than it would be if the warm ocean just had to sit against the atmosphere and passively transfer that energy through conduction or even convection in the surface layer. So this evaporation is like the most efficient thing. Think of how we cool our bodies when we're hot. We sweat. It's the same idea. We are shedding the heat. In this case, the ocean is shedding the heat that way. But what it does then is this huge injection of moisture and energy essentially into the lower atmosphere. And really there's two things going on. So there's two things that lead to this warming, as I mentioned. There's the sloshing and there's the shutting off of the cold water upwelling. And now, in terms of the global climate impacts, there's two key things that happen too. The most obvious one is just that this massive injection of energy and moisture into the climate system is global in scale. We will see probably the Earth's average temperature rise by about 0.4, 0.5 degrees Celsius, so close to a degree Fahrenheit just this year. And that doesn't sound like a lot, but if you compare it to the amount of global warming that we're also worried about to date, that's on the order of 2 degrees Fahrenheit or
so. I was looking at one of the websites that you have recommended recently, the dashboard, the climate dashboard, the climate brink dashboard. And the main page, it says this year's on track for 1.6 degrees C above pre-industrial era. And if you add the 0.4 degrees of heat from El Nino being released.
Well, so next year, so some of that 1.6 is actually including the early effects of El Nino, but next year is where things get really dicey, because actually going into 2027, there's now a very high likelihood, in fact, it's almost certain, that next year is going to be the warmest year on record, because we're probably going to go beyond 1.6, because a lot of this excess heat, it takes a little while for it to get fully converted into global temperature. So that's actually going to happen next year once this El Nino event is fading. We haven't even gotten to the peak, and this is going to happen after it begins to fade.
Okay, so there are kind of these latent effects as a result of, when we measure, where we measure.
Of the global average temperature being temporarily elevated, yes, that's actually going to probably be maximally extreme next year. But what happens in terms of precipitation, that's a sooner thing. That's going to happen probably this winter in a lot of places. And that's sort of the second effect that I was going to talk about. So we have this global redistribution of heat and moisture accelerates the whole global hydroclimate cycle. More heavy downpours, more dry events, more everything in between. But it also disrupts the actual spatial pattern of storm track. So there's both a zero-sum game involved and a non-zero-sum game all at once. So essentially the non-zero-sum game, meaning that it's not haves and have-nots. Essentially, the whole cycle becomes accelerated. More heavy downpours in general around the world. But the storm track shifts usually mean that some places get wetter and some places get drier. And this is because these big tropical thunderstorms that usually develop in the Western Pacific, where usually it's much hotter, are instead occurring in the Central Pacific or even the Eastern Pacific. And you can kind of think of these big tropical thunderstorms like ripples in the atmospheric and the global atmosphere. So they sort of serve as these catalysts for sort of setting the stage for storm tracks, high and low pressure systems, defining where jet streams end up. When the position of these huge tropical thunderstorm complexes shifts by a couple thousand miles, it completely redirects the global storm track. And that is what really is potentially going to be a big deal in California this winter.
And so, and if we're talking about where in California, we've got coastal California, we've got inland California, we've got the mountains of California. And this is, the topography of the West generally, from Northern California up to, from Central California all the way up to Washington. And so do we have differential impacts that communities should be paying attention to and kind of looking out for this year? I guess while we're talking about, we hadn't really gotten back to the main reason that I asked you to the
Yes,
show,
that's
which
right.
is which is that you've been talking about this, and I've been following it for a bit. I first came across you on Twitter back before it was X, and have been following your account for many years. But this year you have been trying to do information damage control, and Blue Sky is the place where I've been seeing you post your work. And this year you posted this week you posted a one pager that you've developed about this potentially historic El Nino event. And so I guess the question is, as we're taught before we get into what specific communities should be concerned about, is what is the main thing that is contributing to making this a potentially historic, and what uncertainty do we have there event?
Yes. Thank you for the reminder. Yes. So the reason why we're even talking about this right now, really, is not because this is just any old El Nino that happens every 2 to 7 years on a semi-recurring cycle, which they do. It's because this particular event is already very strong. It's already essentially among the strongest that we've ever recorded as of, this conversation in late August. And we actually now expect it to become the single strongest ever recorded by a significant margin. So we're near record breaking today and expect it to become unambiguously record breaking in the months to come. So what does that actually mean? What do I actually mean by historic or record breaking? Well, because El Nino is defined by how warm, relative to usual, the eastern equatorial Pacific is. The short and kind of uninteresting answer is that the eastern tropical Pacific will be warmer than it has ever been before, and therefore the El Nino event will be record-breaking. But beyond that, that is true, and it is important because we all know that global average temperature is actually very important, and so is regional average temperature. But the other thing that's going to happen is that the blobbiness, the relative warmth of the eastern tropical Pacific Ocean relative to the rest of the Pacific Ocean, so the degree of warmth in the eastern tropical Pacific will be really extreme, even relative to all other El Nino events historically. So not only do we're headed for the warmest water ever observed in this part of the ocean, but it will also be relatively warmer than its adjacent regions to a degree we haven't seen before. And the reason why that latter point matters is a little bit subtle, but it's actually not subtle on its impacts, because that is what drives storm track shifts like those that we are worried about in California. So it's not just how warm is it, but it's how warm is it relative to other places. So you could imagine that if the whole world were uniformly 1 or 2 degrees warmer, we wouldn't have that effect. But if one region is much warmer than adjacent regions, then things really go haywire. And that's exactly
is this just following basic physics principles of gradients, where if you have a higher differential, you'll have greater flow from one region to another? Is that?
In this case, it's actually even weirder in the sense that there's even more links in the concatenation and the daisy chain, the Rube Goldberg machine, whatever it is that we wanted to describe, sort of the downstream effects of El Nino. But it is related to the gradient. So the concept of differentials and gradients is key. But it's sort of a second and third order effect of that gradient. And it really tells us that essentially the location where these big tropical thunderstorms form really dictates the part of the Pacific Ocean basin where that jet stream is very strong. And in a typical winter, it's actually not that strong near California most of the time. It's strong way out in the West Pacific, but we only get the dregs in a typical winter relative to usual. In a winter like this one, we're probably not only going to be getting the dregs. The strongest part of the Pacific jet stream might actually be right offshore of California. And that's a pretty big difference from what we typically would be seeing. And so that's sort of why this matters. Because, in practice, not only do we get the amplified global warmth, probably record-breaking global warmth late this year into next year, not only do we get acceleration of the global hydrologic cycle, but we get these regional flood and drought impacts that will be at the very upper end of what we've seen historically with El Nino events, and quite frankly, possibly beyond it, because we've never seen an event of this magnitude in modern meteorological history.
From a meteorology perspective, when you have massive amounts of warmer, even though it's winter, warmer air, rain, precipitation coming into, say, California. It's great along the coast, rain, at Central Valley, rain, but you hit the mountaintops where you're supposed to get snowpack. What's going to be happening there? Are we not going to get snowpack? Are we going to see I guess the perpetuation of drought conditions because the precipitation and warmer temperatures will keep snowpack from growing and giving us a water base?
It's a great question because there's two really strongly competing effects, and we actually see this in pretty dramatic fashion in the Western US in recent years, where the obvious one I'll start with first, which is that when it gets warmer, you have more rain and less snow because you're on the wrong side of freezing more often in more locations more of the time. You might get a 33 degree in rain instead of 30 degrees in snow with a couple of degrees of warming. But because of what I like to call the expanding atmospheric sponge effect, which is an analogy my colleagues might have begun to use to describe the increased capacity of warmer air to hold water vapor, so a higher ceiling on how much water vapor can be in the air, when it's saturated, when the relative humidity is 100%, when you're in a cloud, when it is precipitating, by definition, you're saturated, then you actually have more moisture in that air mass. And so there's this interesting Goldilocks situation where if you are high enough up the mountain slope, where it used to be really cold, well below freezing during a typical winter storm, let's call it, 25 degrees Fahrenheit, and say it's warmed 3 or 4 degrees, which it has in many places, that's a significant amount of warming. Well, in that particular location, say you're at 10,000 feet at the top of the chairlifts at Lake Tahoe or something, it's still 31 degrees. So it's fully 3 or 4 degrees warmer, but you're still below the freezing line. Now you've got about 4% per degree Fahrenheit more moisture in that atmosphere. So you can actually get much heavier snowfall because it is warmer. And this may feel counterintuitive, but it actually explains why places along the Arctic Ocean shoreline, for example, are seeing more snowfall in a warming climate, because warmer air, more moisture, and ironically, more open water, because there's less ice and there's more ability for that moisture to actually get into the warmer but still sub-freezing atmosphere. Same thing is true up at 9 or 10,000 feet, where we're actually seeing snow events that are just as heavy as their historical counterparts, if not heavier, despite this warming. But the problem is, in a place like California or Oregon or Washington, there's not a lot of land at that elevation. Most of the mountains, most of the ski slopes even, are more like 5, 6, 7,000 feet rather than 10,000 feet. And at that elevation, historically, a lot of historical snow events were occurring right around 31, 32 degrees, so right at that marginal freezing zone. And now, with 3 or 4 degrees of warming, we're more often than not on the wrong side of that. So we're seeing this interesting elevational gradient. We're losing tremendous amounts of snow at lower elevations. And unfortunately, just think of the shape of a mountain. There's a lot more volume at lower elevations.
At the bottom,
than at the top. So we're losing net snowpack in that way, but we may not be losing as much up high. So long story short, what I think might happen this winter is it's pretty likely that we'll see it wetter than average winter in California. Potentially much wetter than average. We can get into that if you want, but the odds are stacked about as strongly in favor of a wet winter in California that I think is physically possible from a predictive standpoint. I don't really think there could be a stronger predictor than this magnitude, whatever we want to call it, extreme, super El Nino. I'm okay with any of these superlatives. A lot of
I was gonna wonder. I mean, there's like the if we use certain words, it might make it it makes it too exciting, right? It's the
I sometimes feel like there are some scientists who are like allergic to relevance. It really it almost is like a learned. I don't know. It's interesting. I mean, is super El Nino a scientifically defined term? No, it is not. There is no formal quantitative definition of it. But if it is used in the context of an El Nino event that greatly exceeds even the very strong events of history, then I mean,
it's accurate.
Okay, we could find some other word for it, but that's very ivory tower-ish if we decide that it needs to be the superlatively anomalous El Nino rather than super El Nino. I mean, okay. So I'm fine with super El Nino in this case because it really matches the superlative. But I think what might happen in terms of snow is at least we might have this remarkable elevational gradient where we, just by virtue of global warming, it's just warmer than it used to be. And El Nino doesn't necessarily make it greatly or colder. The long-term warming trend is probably a larger margin than the degree to which El Nino will make it, change the temperatures this winter. We may see a lot of snow at very high elevations, and then a lot of rain and not a lot of snow at elevations that historically might have seen a lot of snow. Doesn't mean it won't snow in Lake Tahoe. I'm sure there'll be at least a couple of snow events, but it does mean that we're more likely to be on the wrong side of the freezing line for more of the mountain. We could get incredibly heavy snowfall at very high elevations. And so there's this interesting divergence there.
And this leads into all sorts of, when I think of it systemically, for society, it leads into all sorts of questions about, how do we plan and manage for, are there going to be more super El Ninos? What about more wet winters that have just the snow at higher elevations and not at the lower? How do we manage our water needs? How do we, so I mean, I know you look at societal aspects of, these climate and weather issues as well. So do you have any thoughts on what are we going to do?
Yeah. Well, first
in the West,
and answer your original question of the day, actually, and say, okay, what's going to happen with El Nino?
Yeah.
One is that we know that El Nino interacts with global warming. All El Nino events are unfolding in the context of a rapidly warming climate that is already experiencing more accelerated hydrologic cycle and warmer temperatures. This year's is concerning partly because it is occurring after about 1.5 degrees Celsius, about 2 degrees Fahrenheit of global mean warming. That's part of the reason why this event is going to be such a problem, because it's kind of like going up to the 9th floor. Now El Nino is going to get us to the 11th. Yep. But the actual science on what climate change is doing to El Nino itself is surprisingly uncertain. And the only thing that really appears to be pretty clear at this point is that the most extreme El Nino events will probably become more extreme. Just by virtue of the fact that, again, El Nino is this heat release mechanism and we're cramming more and more extra heat into the tropical oceans. But whether it will do so because we increase the frequency of all El Ninos or just the extreme ones remains to be seen. And some interesting thing that's happened so far is you've actually seen more La Nina events historically, but also more extreme El Nino events. So we're kind of spending more time on the opposite end of the compressed spring, but we're letting it release more and more violently. And that would probably be the most disruptive version of the future, which of course means it's probably the most likely because it's 2026. And that just seems to be how things are going these days.
Yeah.
But we don't know for sure. And it's a really active area of research because it's critically important. Now, all of that said, we do know, the big picture. It's getting warmer with less mountain snowpack overall. We're starting to see more variability, bigger swings between good and bad snow years, and frankly, more variability between wet and dry in general, this notion of hydroclimate whiplash. So regardless of what happens to El Nino will contribute to that. In some years that will be a major contributor, in other years less so. But the overall direction is sort of more variability, more whiplash when it comes to hydroclimate. And interestingly, this is something I've had to put back on
drought, super, like on the West, we talk about pineapple expresses all the time.
Yeah.
Is it just going to be like drought conditions and pineapple expresses?
So yeah, we sort of lose the middle. Another societal conversation where kind of the missing middle is very much what we expect to see with wet and dry events. So not just precipitation, but especially if we consider the full spectrum of precipitation and evaporation and the whole water cycle on the whole, more extreme downpours, but fewer of them, and more extreme evaporation in between them. So, the expression, when it rains, it pours, you can just kind of extend it. Now, increasingly, when it rains, increasingly, it pours. And so this is why we can't look to changes in average precipitation. We don't see much of a change in average precipitation in California. We may not have much of a future change in average precipitation. And some have taken that to mean that, well, California, water isn't going to change very much. It'll get a little warmer and then the rest of it's the same. That's not at all what we think. It's not at all what we're experiencing. And it actually makes a pretty big difference in terms of how we manage some of these changes. Because if you plan for a future where it's exactly the same historical precipitation distribution, and that's how you interpret no change in the mean, versus a huge increase in the wettest events and a large increase in the driest events, you're operating in a completely different environment in terms of managing and sort of mitigating the risks of drought and flood and all these things. And so, the first step is to to make sure we're measuring the right thing to understand what we actually need to be adapting to in the first place.
And I guess that's one of those questions of, which science, which research are you doing? Are we trying to solve a societal problem of the drought conditions and water availability in the Western US? Are we trying to solve for the safety of coastal populations with rising sea levels or with erosion from greater storm surge? They're different problems, but all part of that same water cycle, climate change system.
And it becomes really difficult to disentangle some of these things. I mean, in my job, sometimes I'm context switching constantly between actually walking people through specific disasters in real time, sometimes minute by minute, and then taking a step back and then launching myself into coding and writing and figure plotting for a few months, and then moving on to sort of talking about that work and integrating it in different settings. And right now it's kind of super El Nino all the time. That's going to be the media blitz probably for the next 3 to 6 months. I'm clearing my calendar.
Which I'm so glad that we got tonight.
It's already full again, but it is, I think, most scientists, I think, it's not true of everybody. You obviously can't speak for everyone, but I think most scientists do what they do, at least partly because they think that what they're doing is useful in some way. Mm-hmm. It's a job also, and sometimes it's important to remember that, we all need health insurance too, but and that scientists are people, which sounds like a silly thing maybe for the audience of this particular program, but is a surprisingly bold reminder in some settings.
Even American, with the use of AI now, the majority of scientists are still human.
Yeah. Yes, we are. I assure you. Yeah. And maybe the live streaming glitches are now becoming a valuable asset as reminders that we are very much human. Still, our AI overlords would not make such silly mistakes with dates
right?
and times.
How do we prove our authenticity? Oh, it's the human error.
So it's all strategic. For anyone in the audience, that's entirely why. But
absolutely.
But I think it's I think that this is a real thing. Like the average American can't name one living scientist. And I don't think that's actually the fault of the average American. I think that that's a confluence of a lot of other exogenous factors that have brought us to the point where that's the case. And so I think, part of being available and making yourself available in the world, part of, I think, our role as scientists is to do that. And it's not just to communicate the science, that's obviously important. It's not just to integrate the science with society, but it's also to humanize the scientist, which again seems like a silly endeavor.
Be a human person who does science and is not afraid to talk about it with people.
Yeah. Yes, honestly, yes.
So I was curious about this media blitz and the work that you're doing, and you've obviously been cultivating your presence in communicating science for many years now. How is the media treating the things that you say? Do you feel like the messages you want to be spreading are spreading appropriately, or do you feel like there are misunderstandings that are being caused?
So I'm in a somewhat unusual position where I actually have a truly systematic sample to draw from this.
Nice.
I recently did my 2000th media interview.
Oh, wow.
So I actually have a 4-figure sample size, and this year I've done about 250. So it's, I have enough experience that I have a pretty good sense of like the range of ways that things can go wrong and the ways in which things can go right and how much these things are outliers. Mm-hmm. And I would say that in general, and I've been doing this for long enough also to sort of see the sea change in journalism. I mean, it really has been an alarming decline in my own career over 10 or 15 years. I mean, just the collapse of American journalism, but really global journalism.
And science journalism, even more so.
It's almost in some circles ceased to exist as its own entity. I mean, the number of people who I'm talking to these days who have no background in covering anything that's particularly science related. I mean, I'm talking to sports reporters. I'm talking to, political people who are on Capitol Hill a lot. So I think that it's a challenge. And I think that it's an increasingly difficult environment, which is not really the fault of individual journalists. It's more, again, the large scale environment of misinformation and clickbait media and everything being driven by viewership rather than nuance or accuracy. Nuance is a dirty word in 2026, and I absolutely refuse to let that be the way that I operate. But you do still need to be able to offer sound bites, right? Like you need to have like the 10-word version of what you're saying, the 10-sentence version, the 10-minute version. And I'm not.
And sometimes the 45-minute to an hour
sometimes
version.
You get long form every once in a while. And I think it's difficult sometimes. Some of these things you really just can't get into 10 words. You just can't. And you're asked to I need a 10-second soundbite. And I'm like, I literally cannot do that on the topic that you're asking. But essentially, generally speaking, it's generally a positive experience. That's what I want to reflect, is that across all of these many, many hundreds of interviews per year, thousands cumulatively in a career, in general, the word is getting out about things. And in general, it's more correct than not. Is every single line accurate? We scientists do statistically like to pick things apart. Most of us in general, speaking as part of a group, like to lead with the caveats. We like to focus on the minor errors and kind of miss the
bigger picture.
Sometimes. And often I'm left saying, well, what is the overall? Is this article going to do more to inform people or more to disinform them? And as long as it's net positive, then I'm okay with it. Even now, the one thing that really I get hung up on these days, and this has actually gotten worse in the last couple of years, I think, as ad revenues are squeezed, headlines. Headlines have gotten really, really bad, and increasingly they're just not accurate. They are literally in many cases the opposite. Literally,
they say something, it's emotionally triggering, and the headline is there only to grab people's attention. And this is what we see people sharing on social media.
It's what gets the clicks. It's what the preview banner on social media is. And the irony is that in almost all cases, it wasn't even the journalist that wrote the article that wrote the headline.
It's a headline writer.
In some cases, and it used to be their editors at least might be the ones to punch it up a little bit. Now it's not even the editors. Now it's the social media experts that are literally optimizing keywords for clicks to the point where, and this is a challenge, So not to dwell on the negatives, but I think that.
But people need to be aware of what they're seeing. So I appreciate it.
Yeah. But it is one reason why I spend so much time talking to journalists. I mean, it is a huge part of my job at UC Agriculture and Natural Resources. It's really the only place that's allowed me explicitly to sort of spend that much time. I mean, I was doing it anyway, but now it is officially part of my job, whereas before it was just sort of another 30 or 40 hours a week on top of everything else. It's still 30 or 40 hours a week, but at least it's considered to be something.
It's part of what you're.
But I think that I think the reason we don't see more scientists engaging in that way, first of all, is it's hugely time consuming. And unless it is part of your job, it's very difficult to find the time, because journalist requests, and now I'm going to stereotype journalists, they're almost always last minute at the worst possible time. Just somehow it's Murphy's Law.
Just the way it goes. They saw the news. They know they have to get it, but
last minute deadlines, whatever the case may be. But I just think that it's difficult to shoehorn it into an existing job and be successful, because you do get better with practice, and it's daunting the first few dozen times you do it. And it takes a while for most scientists to have done a few dozen of these. It takes years sometimes. And then I think it's also this fear that what you say is going to get misconstrued somehow. And it is a risk. It does happen sometimes. I would say statistically, 1 in about 50 to 100 interviews, something gets egregiously twisted around in a way that seems conspicuous. But honestly, it's like 95% or 98% not the case. It's literally like 95 to 98% of the time.
That seems I mean, if you were doing, your p-value of 0.05, like you're right, you're in there.
Exactly. This is my point about statistically significant sample size.
Yeah.
I mean, I think it is. I've done enough of these that I think it is something that is genuinely anomalous when there's something that is other than good faith. And I think that is reassuring.
Yeah.
But I think it means that if you're a scientist, you've only done 1 or 2 interviews and one of them didn't go very well. Either that's because you're new to it, or maybe you just got unlucky and you're in that 5% of the cases where things don't go so well, and you just kind of got to keep charging forward.
One of the big questions from a lot of scientists interested in getting into science communication now, specifically since the pandemic, but I know climate scientists have been dealing with it for a very long time, is the politicization and the personal attacks that occur, and the concern that institutions are not necessarily going to have protective measures in place to help the scientists be able to communicate safely in a public fashion. And so have you had, I mean, I went to one link of yours that ended up on X, and there are people there. You know, you are an activist climate scientist with an extreme view. You're pushing an extreme view, Daniel.
Right. Yeah. I keep a running record of I call it unsolicited criticisms. It's a Word document. I just copy and paste things into it. It's been open to, it's 70 something pages long now. I've had it since probably 2007. And it's really just me, just sort of mostly just for my own edification, but occasionally maybe for, who knows if there's any future legal proceedings, but the weird comments, the hate mail, the death threats, whatever the case is, and there's all of the above. And the interesting thing is that a lot of it does relate to perceived political ideology, and a lot of it is, I mean, for other people who don't look like me, it's actually directed in other ways, interestingly. For me, it's directed mainly, what is it? The liberal, commie, elite, fearmonger climate scientist is some combination of those things, sometimes all of the things at once. For other people, it's directed more toward their outward physical appearance or something, or based on their, how
I'm sure Catherine Hayhoe.
Yeah, people's identity, outward identity is often a target. But whatever the case may be, I think the challenge is that there really is not institutional support. I mean, the total honest answer is there isn't. And actually, you're lucky sometimes if your institution is going to even leave you alone. Sometimes there's active inhibition, I would say, and especially now in the last couple of years. I mean, it's gotten to the point where I'm pretty comfortable calling it overt censorship. Not in my case. So to be clear, I'm not talking about UC-ANR, University of California, but I'm talking about colleagues in a lot of other places who have been quite directly told, do not say these things, do not use these words, really don't even talk to the media at all unless there's a PR person literally sitting over your shoulder. I was recently interviewed as part of a documentary on the history of the National Center for Atmospheric Research. Where I do have a desk, but I'm not employed by them in any way.
And is this the National Center for Atmospheric Research, which was going to be shut down?
Yes, and that's still a risk, but they've sort of gotten a bit of a stay of execution, thanks largely to genuine, pretty effective community organizing and some fairly effective regional and state leaders. It's not a done deal. It's still very much at risk, but it's still there. Everyone's still there. Yeah, still operating. But there's a big but here. One of the outfalls of this is that they essentially couldn't get any of the NCAR climate scientists to speak on camera about climate change. Right. Because they had essentially a PR media handler in the room, just off camera left, standing there.
And basically going, nope, you can't say that. Nope.
Or talking about
just targeting,
the intersection with partisan political politics, which unfortunately, to my great regret, is a very relevant part of that story as to how NCAR got to be threatened in this way. And as has since come out over the past week, that there was literally an email in which it was asked, what are the ways we can punish the state of Colorado, where NCAR is located, for putting Tina Peters in jail. So essentially, the
Wow.
county clerk who interfered with the election, who was convicted of this by the Republican Attorney General,
Yeah.
actually jailed. This was retaliation for that in writing, in government emails that are now subpoenaed. So this was speculation at the time. It turns out to have been literally the case. Like,
it was a huge, I mean, that was a huge question. I remember when the announcement was coming out that this is a basically supported, nonpartisanly supported government, like NCAR has been around for decades. It's like everybody supports it. It's been doing great work. And the question was why? What happened?
So this is part of it. And the other part of it is another partisan political thing that I wish wasn't relevant, but is, which is Russell Vogt and Project 2025. This was explicitly something that is in that policy.
Yeah.
What has become a policy blueprint document, which was described as such, and I don't think too many people took it seriously. I don't quite know why at the time.
I did.
I was
very worried.
Yeah, I mean, I was running live streams, in the September and October before the election, reading verbatim from the section in Project 2025 on weather and climate and why NCAR would probably be a target in this environment. And then, so the broader point is not to get too off topic, but it's really that it's become impossible to separate these things. And I think the argument that science is not political was never true. Science has always been political because it intersects with people's lives, and we make decisions about how to do things that are hopefully informed by science, but those decisions are ultimately political ones. But partisan politics is a little bit different. A lot of these things, it is true that in the past, there have at least been periods where a lot of these things were not as partisan. They were still political. Now it is also overtly partisan, which is really unfortunate, but then it sort of becomes a denial of reality to pretend that it's not.
We are at this point right now where if I could have one wish come true, it would be that people would stop denying reality and that we could get back to actually, having real life and doing the work. But in the sense of the science that you're working on, and maybe specifically El Nino, is there anything that you see over and over again that is a misperception, a misunderstanding, whether for propagandist or just misunderstanding kind of reasons that you would love to correct, that you'd love if people could stop having to have this thing repeated over and over again? Well,
and it's going to be a general topic because I actually think it does work both ways. Where this is the origin for a lot of different conspiracy theories. It's a lot of reasons. It's an origin for people wondering why we don't implement A or B obvious simple solution to solve X. It's a reason why we need all of these seemingly infernally complicated weather models and supercomputers and these massive systems of observations, which is to say, it is very difficult to trace cause and effect in the Earth system. We cannot say you do this somewhere in the world on, a day 6 months ago, and the effect 6 months down the line somewhere else on Earth is going to be Y, unless we have some really sophisticated ability to model the whole Earth system. That sounds very abstract. So let me give a few specific examples of why this ends up being so important. One is, and this has been in the news a lot recently, I don't know if you've seen these stories about people believing that the government can control the path of storms, or is redirecting hurricanes, or strengthening hurricanes, or for whatever strategic, military, political reasons. It's not necessarily that I trust the government, of any government, that they wouldn't do it if they could. Right? It's more than I trust the physics of the situation that make it impossible to do these things. And part of it is simply because we do not possess the ability to understand, even if we had essentially magically powerful tools, space lasers or whatever the invoked technology is in these theories, we do not have the ability really to understand what it would actually do to any particular storm. You could maybe imagine some sci-fi futuristic James Bond villain level space laser that could be bad, but would it be able to control the path of a hurricane? Please explain to me.
It would have to be a very strong space laser to be able to heat the surface of the ocean in a very specific path with the appropriate energy to maintain the storm.
Is that even if you could do that, yeah, how would you guarantee where the storm is going to go? Now you also have to control the trade winds blowing between Africa and the United States. You also need to control the amount of dust in the vertical atmospheric column, the amount of Saharan dust. You need to control the vertical distribution in temperature across a 3,000 square mile area. So at that point, any technology that would be profound enough to affect storms on that level would be so dramatic it would probably just destroy the earth. So it's not.
So let's not go there. Yeah.
but my point is, it's not so much that we wouldn't dare do it. It's more that we can't, for better or for worse, probably for better after all that. But that we wouldn't even be able to know exactly what effect that was going to have. All you could say is this is going to do something dramatic, but not it would move this particular storm to this particular location, or it would intensify in this particular predictable way. Ironically, the most direct way that we're influencing the weather is by warming the climate. So we are, in fact, influencing all storms on Earth, but not in a way that we get to exquisitely control their specific path, intensity, or position, or anything like that. We're kind of just, we're just sort of throwing all that extra energy out there and seeing what happens. So that's one thing, is we can't exert that level of exquisite control, not because we wouldn't if we could, but mainly because we do not fully understand cause and effect to the level that we could even achieve that outcome if we possessed that near magical level of technology. That also explains why unintended effects can arise even from well-meaning interventions. So we have all these people saying, let's green the deserts, let's plant forests, let's refreeze the Arctic, let's put huge phytoplankton blooms in the Pacific by dumping iron or something.
Let's bring mammoths back.
Let's bring mammoths back. Let's whatever it is. And while these at least maybe aren't coming from a place of James Bond level villainry, they're intended to solve a societal or ecological problem. The problem is there are so many unintended consequences, and they're not subtle. When we, for example, model what the effect of removing a forest, like a 200, 300 square mile patch of forest in the Amazon or in the Canadian boreal forest, or adding a patch of forest as has been proposed to the Sahara Desert by pumping in a bunch of water from the Mediterranean. These things do weird things like cause droughts in the Great Plains of North America, or screw up the monsoon in India, places that are just very far away and you might think are indirectly connected. But the point is, like, you change something somewhere and you've probably changed something very different somewhere else in a way that is not intuitive at all to our human brains. And you can kind of get there.
The quantum butterfly wings flapping, right?
Yeah, I mean, there's
a bit more.
And then, that's a whole nother problem. So now we have companies out there, and there's a New York Times headline that a company claims it's going to solve the Western water crisis by doubling the flow in the Colorado River through cloud seeding. And
really? Yes. Well, cloud seeding with the silver particles or sulfate particles, like people have been wanting to do this for a while. They've wanting
to do it. And succeeding in doing it. Yeah. Two very different things.
And succeeding in doing it to the extreme that is necessary to double the water flow through the Colorado.
So far as we understand it, it's not even theoretically possible to do so. The theoretical limit on how much you can really augment clouds through cloud seeding, for example, is on the order of like 10%. It's not very much. And so, frankly, I don't know where they're coming from. And it's clearly ludicrous, and also misunderstands the problem, which is actually, a lot of it is not lack of precipitation. It's too much evaporation.
Yes.
So how are you going to solve that one?
Too much evaporation, and also water rights that have allowed for different groups taking more water in different places. And it's a whole system that is so complex.
Exactly. So it's hubristic and not scientifically plausible, but also just misunderstands what the problem is, which is that it isn't even just a physical science problem. It isn't just a climate change problem. It is those things, but it's also that we grow alfalfa in the desert, and we signed the Colorado River Pact in a window that was unexpectedly wet. It turned out it was pretty uncharacteristic of the region, and we just happened to sign it in that wet window. So I guess my broader point, just to bring it back home, and there's interesting little bits and pieces, is that it's none of this is maybe as obvious as it seems. There are reasons why we have these systems in place that seem overly complicated for prediction and for projecting into the future and for trying to understand the causes and the effects of either interventions in these systems or disruptions to these systems. El Nino, maybe this brings it home, is a really good example of a pretty localized perturbation. This is something that's only happening initially in the eastern tropical Pacific Ocean, in a relatively small patch of water, a few hundred miles on a side for the most part. It's a little bit bigger than that this year, but it's, in the scheme of things, it's not a very big patch of ocean. But it is a really important patch of ocean when it does what it's doing right now. And I think that that's a good example of how, these cascading effects all around the world. This patch of the eastern tropical Pacific Ocean could lead to floods in California, could help partially, temporarily, for a little while at least, alleviate the Colorado River water crisis, could lead to droughts in South Africa, floods in East Africa, could disrupt the Indian monsoon, could reach a record-breaking heat and wildfires next summer. So we're already talking about a year ahead. So it's this profound influence from this little patch of water in the East Pacific, in a very remote part, I would add, of the East Pacific Ocean. The only populated island is the Galapagos, and there aren't any other people out there.
Yeah, that's populated by lots of animals.
Lots of animals, yes. Partly by virtue of the cold
occasional
water
tourist.
upwells. Yeah.
Yeah, the Galapagos are just, one of the most, as a biologist, it's one of the most amazing spots on our planet. And I do wonder, these El Nino events, the heat that the oceans are going to be having, and we don't need to answer all these questions, and we probably can't, but, the impacts over time of these extreme events, how will they impact isolated island populations of animals, of people? How will they impact the localized communities where they're occurring? I think these are the we're anthropocentric, but at the same time, if we can take care of ourselves, maybe we can take care of the planet too.
I hope so.
I do hope so.
That's certainly what I would hope, and part of it is just thinking about the whole planet as a system, and that you can't escape your problems by going somewhere else.
Speaking of escaping, someone asked earlier if mountaintops, the really high mountaintops, are the places that the billionaire bunkers should be built now.
Now I have to answer whether I think billionaire bunkers should be built.
No. We're not going to answer that question. If you were building a billionaire bunker to survive through, however many years,
well, let me put it this way.
Where would you build it?
Let me put it this way. The places where the billionaires are actually building their bunkers is not where I would build mine if I were the type of person to have $1 billion and to be in a mindset to build bunkers. And neither of those two things is true.
Are happening. Awesome. Thank you so much for joining me tonight. Is there anything that we've covered a lot of ground, a lot of the El Nino and some extra information in there, but is there anything that, if there's one thing you want people to understand about what's happening right now, or just one message that you want people to take home?
Yeah, I mean, in terms of El Nino, I think this is a big one. It might even be the big one of our lives. And what does that mean in practice? Well, it depends where you are in the world. If you're in California, as I suspect a fair bit of the audience might be this evening, then it really does mean that the odds are shifted significantly towards a wetter than average winter this year, and maybe even a very wet one that would carry an increased risk of flooding. So it's a good year to consider flood insurance. If you don't have it, fewer than 2% of Californians do, so it's a very low number. Majority of those in floodplains do not have it of particular note. Or even more basic things like clearing your gutters and your culverts and making sure there's no suspicious cracks on hillsides near where you live, things like that, basic things. Also coastal flooding. So El Nino will result in a temporary elevation of sea level by about 1 foot. So it's almost like a sudden doubling of global warming related sea level rise this year. It will go back down next year, until it rises again because of global
Again.
warming. But this is a temporary, essentially like a doubling. So king tides, potential for big time coastal flooding, major disruption, not just along the oceanic coast, but also the bays, San Francisco Bay, Monterey Bay, Humboldt Bay, San Diego Bay. And this could be a significant problem for a lot of people, around California and other parts of the world where there's similar temporary elevation in sea level from this. So that's a very California-centric perspective. There will be other disruptions in other regions, but this is about as big as they come in terms of El Nino, and that doesn't guarantee historic impacts just because El Nino itself is historic, because of all the other concatenating factors we've just been talking about. Other factors are at play. They can amplify or offset. But let me just put it this way, El Nino of this magnitude is like a person shouting through a megaphone in a crowded room. A more ordinary El Nino event might be somebody like kind of speaking at their normal voice in a room with 100 people. You can hear them if you're close by. You're probably going to get drowned out if you're farther away. But this year, that person with the quiet voice has got a battery-powered megaphone.
And it's standing on a table.
Yes.
Yeah. Oof. So, yeah, there's a lot for us to think about this year, but I really appreciate you taking the time to clarify some of the science behind the El Nino event and the phenomena as it occurs in its oscillations, and also for this very specific event that we are looking at this year. And yes, while there is some uncertainty, the certainty is that it's going to be a lot.
It's going to be another one of those years, and we'll learn some things scientifically, and I'll just keep my fingers crossed for a minimum of harm. Let's say that.
Yeah. May all of us hope for a minimum of harm to a minimum number of people, homes, etc. Thank you so much for joining me tonight. Where can people find you? We've got you at your blog.
Yes.
Where are you online so people can find you and search you up?
Very online. People have various opinions on whether that's a good or a bad thing, but I am very accessible, available on most any platform. The ones I'm really emphasizing these days, as you mentioned, the Weather West blog, weatherwest.com. My YouTube channel, where I do less well-produced live streams than you do, at Weather West. They are, as you'd expect, mainly weather and climate focused, occasionally elsewhere. And then also on Blue Sky as well. And, if you're a LinkedIn person, you can find me there and some other places too. But I would say Weather West blog, YouTube, Blue Sky, the mainstays these days.
Wonderful. I hope people do follow you if they are not already, because you have and continue to put out amazingly helpful, useful information that it just clarifies things. And so I just really appreciate the work that you do. Thank you for your service.
Well, thank you, and likewise. Part of the half the battle is just having these conversations in the first place and finding forums to have them. So
let's have more of them, and I know you plan to. So have a wonderful night. Thank you so much for joining me, everyone. Dr. Daniel Swain, he is Weather West online, and I recommend that you check out his YouTube, as there was a wonderful webinar that he put out this last week or so talking about the El Nino event. Another one that he's done more recently talking about warming in Southern California. There's some just great information in there if you want to spend some time rabbit holing. So.
Thank you. And yes, keep it going.
We will. Thank you very much for your time. Have a good night. Everyone, this is This Week in Science. I am Dr. Kiki, and tonight I thank you for joining me for another episode with this wonderful interview with Daniel Swain. What fun talking about a very serious subject, actually. I mean, there is a little bit of excitement and joy in there. There's we can learn things from this historic event that's coming. And there's a side of the scientist and the researcher there that is very optimistic about what can be learned. But in the process, we must always keep our awareness of what is the reality that's happening on the ground. Thank you for joining me tonight. If you are interested, check out This Week in Science every Wednesday night, 8 p.m. Pacific time. We live stream like we are right now to Facebook, Twitch, and YouTube. You can find us looking for This Week in Science. We are online on social media at TWIS Science. We are also on just about every podcast platform that's out there. So if you want to listen to this as a podcast, please look for This Week in Science on your favorite podcast platform. Our website is twis.org, and that is where you can go to find our Zazzle store link if you're interested in any TWIS merchandise. It's one way that we support the show. It is we are listener supported. We do not take advertising. I have always thought that a listener forward approach is the best way so that we can remain unbiased in this media field where we do not have any advertisers that we have to please. It's all about you, the audience. So if you are interested in supporting independent, listener-supported science media, head over to twis.org and click on the Patreon link as well as that Zazzle link. Patreon is the community that we use for the crowdfunding of our efforts. We can't do it without you. Thank you for your support. Thank you for believing in curiosity and information that's free. All right, everybody. I do have no animal corner. I'm sorry about that, but it is time to talk about a few other science stories before we leave for the night. They're going to be quick so that I don't want to bore you with all this news. If you've ever wanted to lie around and get the benefit of exercise without actually exercising, apparently there is a research study that has come out in Nature this last week where the researchers have essentially developed muscle grafts of self-stimulated pulsating muscle tissue. The study is entitled Contractile Myografts Confer Systemic Anti-Aging Benefits. And the caveat here is in mice. Okay, yet again, in mice. So myografts, that is muscle grafts. These researchers publishing in Nature Aging developed subcutaneous transplantation of differentiated autologous myocytes, muscle cells that are autologous, so from the patient. So they are personalized medicine. So they had mice that they took muscle cells from, grew muscle cells, and created these muscle grafts, myografts, that were implanted subcutaneously, so on their backs, underneath their skin, and they pulsated. They were constantly pulsating, kind of moving around a little bit. And the mice, older mice, any mice that had these pulsating myografts, oh boy, yeah, well, they got the benefits of exercising. They did not have as rapid aging. They did not show the metabolic signatures of non-exercise, that normally come along with aging when you don't move or exercise. So the idea for these muscle grafts is, of course, it's not going to work the same in a mouse as it would in a human. Scale is completely different. And where these myografts improved whole body muscle mass and function, metabolic and regenerative outcomes in aging and obese mouse models, according to their abstract, this would be more difficult to make work in people. And you'd have to put it all over your body. You'd have to implant it in lots of different places. And so the people who would be most likely to need the benefits of exercise, who cannot exercise, those who are bedridden, who are paralyzed, unable to move, you'd have to poke them a lot to be able to implant enough of these pulsating muscle masses to potentially have the impact on the whole body aging process in humans. So that's one of the big questions, is how would this really work in people? Could it work in people? But yeah, pulsating muscle masses. It I don't know if I could handle it. It would be like having a muscle twitch that you couldn't control, because it would constantly be moving under your skin all by itself. Yeah, one by land, two by sea. This is not exercise pills. This would be little exercise implants. Next story. Let's talk about. Let's talk about an issue in science. We have talked about many stories over the years related to a compound called beta-galactosidase. Beta-galactosidase has been identified by multiple studies and used in hundreds of studies, antibodies for it, to be able to identify it within cell cultures and other work looking into the metabolism of aging and senescence. And so senescence is this process where the cells shut down. And it's a common process of cells during the aging process. We have senescent cells all over our bodies from the minute we're born, and more of them, I guess, as we get toward death. But one of the questions is, how can we improve the health of our cells for longer periods of time so that we reduce those the need for those senescent cells? Beta-galactosidase in mammalian models has been identified and been used as a target over and over and over again. This summer, a researcher, Sholto David, he's a UK-based molecular biologist, he came across a study that used a beta-galactosidase for E. coli instead of the mammalian beta-galactosidase. He looked at that and went, that's not going to work, right? Because the bacterial galactosidase antibody would not connect to a mammalian galactosidase in the same way. It may not give the same signal. And he went on to look further, and on August 21st, Nature reported that there are more than 50 papers on cellular senescence that seem to have used bacterial E. coli based beta-galactosidase antibodies as opposed to the ones that are targeted to mammalian proteins. So the question is, what difference did it make? Does it make? Do these studies need to be revalidated? There's big questions in this field right now, but we're looking at the possibility that there are hundreds of papers that have been affected by antibodies like this, where researchers have not validated their antibodies and are using an inaccurate antibody in their study and potentially getting the wrong signals. So it's a big question, and it's a big story that came out, and it's potentially impacting the field of aging science, but we don't know for sure how it's going to play out yet. There are many researchers who have been contacted. Some researchers say, yeah, I did use it for some experiments, but they didn't necessarily, those experiments didn't have any say in this particular result. So, there's a lot of question as to what the outcome of this will be, because there are teams looking into revisions, into recalling, retracting papers, and lots of groups for research integrity are really taking a look at this, because it could be an issue that impacts a lot of science. So why don't we have systems where people have a better way of validating their antibodies and making sure they're using the right ones? Come on, people. Oh, and one of the things that's been brought up by many individuals is that the ongoing use of artificial intelligence, LLMs, to develop ideas and directions for scientific research could actually make the problems of using these beta galactosidases worse, because if they're basing everything on the improper use of an E. coli antibody as opposed to a mammalian antibody, it's going to just keep on going. And I don't know, it could make science worse. Yay, artificial intelligence. For those of you who were babies once upon a time, we all were at one point or another. If you were never a baby, I would like to know how that possibly happened. Researchers just published an open access paper in Cell Reports on what they call retrosplenial cortex maturation aligns with the transition from infant forgetting to persistent memory. What does this mean? Well, what this means is that I'm going to put a picture up on the screen right now. What this means is that the researchers who published this paper were trying to figure out why we can't remember our baby experiences. Why do we forget that period of time after birth until we're about 2 or 2.5 years old? And there have been questions about what parts of the brain are mature enough to be able to handle the conditioning of memory, the collecting of memory, the where we put it. And so this particular study, they were able to focus on the retrosplenial cortex. This is important for adult memory consolidation, but nobody's really been able to understand the role that it plays during development very well. And so they were like, hey, maybe this is important for memory recall. If it's important for putting the memories somewhere, consolidating them, maybe it's important for allowing us to recall them as well. In the mouse models where they studied the retrosplenial cortex, they showed that the timing of when the retrosplenial cortex is starting to be active and when they get like specific dendritic spines where the dendrites are connecting with other neurons and starting to make connections, it's really about the developmental trajectory of the retrosplenial cortex. It is not mature enough, at least in the mice. It's not mature enough at the time up until about 2 years, 2.5 years, somewhere around there. And of course, there's going to be variation from brain to brain to brain. But that infantile amnesia is not that the brain couldn't recall it if the memories could be consolidated, but that the retrosplenial cortex wasn't working. It didn't make the connections yet. It didn't have all its dendritic spines. It wasn't ready to take the information in and consolidate the information where it needed to be so that it could be recalled later. So in effect, with the way the hippocampus works, the retrosplenial cortex, all the things working together, in effect, because the infant brain is not mature enough or connected in the right way to allow for these network connections that allow that network of neurons that is a memory to be put in place, that's why we have amnesia. It's because the brain, it isn't writing it down yet. That's pretty much it. The brain doesn't have an eraser in it. It just never had the tools to write it down until it develops at the right point in that infant development. Okay, last story. It has to do with older adults. If you had chicken pox, I did. You might, you probably want to get that shingles vaccine. And we've talked several times about the benefits of the shingles vaccine to individuals. And apparently there is a new study out. It's news is out all over for this. If you have been putting your shingles vaccine on the slow burner and been waiting to have it done for individuals over 50 years old for whom shingles can be a problem. There is a vaccine called Shingrix, which is it's known as a recombinant vaccine. And this recombinant vaccine, Shingrix, based on the records of 70,000 people in the United States, has found that there's a 12% lower risk of cardiovascular diagnosis, cardiovascular disease, heart failure, heart attack in individuals within 3.5 years after getting the shingles vaccine, that there's a 12% lower risk of these heart cardiovascular diagnoses if you get the Shingrix vaccine. Zostavax is the first vaccine that became available against shingles in 2006, and that's a weakened version of chickenpox virus. And Shingrix has newer technology, and it's in the UK is being rolled out, but it has been available for this study in the United States. And researchers tracked adults 60 years and over for 7 years after vaccination. And there's 2 doses, an initial dose and a booster. And by the end of the follow-up, according to The Guardian, and this is published in Nature Medicine this week, the vaccine is associated with a 4% risk of cardiovascular diseases. And so there's the Shingrix being a 12% reduction that is in the first 3.5 years, but by the end of the 7 years, it's a 4% lower. Overall, this is could be a big change for individuals. And if, you don't want to get shingles, it's not fun and that's not good. And if you can have a vaccine that also helps protect your heart, for whatever reason that it's doing that, because who knows? I don't understand why, and they don't either. They're trying to get more definitive evidence as to why it could be protective, and it may be that shingles itself increases the risk of cardiovascular disease. There's also, it could be that the vaccine leads to immune system boosting. So maybe getting rid of inflammation. There are multiple reasons why it could be having this impact, but the bottom line is that this is the first study where they have been able to show in a particular way for not just between unvaccinated and vaccinated populations, but actually being able to compare people who got one part of the vaccine, just the first dose, as opposed to the booster, versus unvaccinated versus, a different shingles vaccine. So this whole population, they're looking at the comparison of being vaccinated before and after the switch from Zostavax to Shingrix in the United States, which happened in 2017. And so if you're older and you have not gotten your shingles vaccine, leaving up some mouse brains for a little bit, maybe you should think about it. It'd be good for your heart. I care about your heart. I heart your heart. And so Aaron Anathema got Shingrix. Wonderful. Yes. Fingers crossed for you. Fingers crossed 3.5 years that, or maybe 7 years, that you will be cardiovascular event free. That would be amazing. Okay, everyone. I hope you sleep on that. I hope I got a little bit of good news in there beyond the extreme event of El Nino information that Daniel Swain was able to bring to the show tonight. I do hope that you all go into the next week being happy and, curious. That's what we try to do here. Thank you all for joining. All of you in the chat room, thank you for your questions. Thank you for your comments. Thank you for thinking and being a part of this audience. I really do appreciate everybody, Twitch, YouTube, Facebook, who come, comment, and are a part of this whole conversation and this community. And thank you for keeping the community a respectful great place to be so that we can all continue to talk to each other about sometimes what can be difficult subjects, but sometimes can be a lot of fun. Fada, thank you so much for your help with social media and show notes. Gord, R and Lore, others, thank you again for your help in the chat room. Identity 4, thank you for recording the show. And Rachel, thank you for editing. And thank you, of course, to our Patreon sponsors. Thank you to Aaron Anathema, Adam Mishkan, Alan Viola, Ali Coffin, Andrew Swanson, Artem, Arthur Kepler, Bob Calder, Brendan Minish, Brian Carrington, Chris Wozniak, Christopher Dreyer, Christopher Rappin, Craig Landon, Craig Potts, Daryl Myshak, Dave Wilkinson, David E. Youngblood, Derek Schmidt, Don Mundis, E.O. Eden Mundell, Eric Knapp, Flying Out, Fredis 104, G. Burton Lattimore, Greg Briggs, Jack, Jason Olds, John Atwood, John McKee, John Ratnaswamy, Johnny Gridley, Ken Hayes, Kent Northcote, Kevin Parachan, Kevin Reardon, Kurt Larson, Lon Makes, Lauren Gifford, Mary Gertz, Marjorie, Mark Hessenflow, Mark Jenkins, Noodles, Patrick Pecoraro, Paul D. Disney, Paul Ronovich, Pierre Velazarb, Richard Badge, Robert Norland, Robert W. Farley, Rodney Lewis, Rudy Garcia, Remy Day, Sean Clarence Lamb, Shu Brook, Stephanie Embry, Stephen Alberon, Steve Leesman, aka Zima Sue, Doster, Teresa Smith, Tony Steele, Vegard Shefstad, and What the If? Thank you all for your support on Patreon. And if you would like to be a part of this list, make sure that you head over to TWIS.org, click on the Patreon link, and subscribe to support us at $10 or more per month. Of course, you can offer any amount. We will take it. All of your help helps. But for those people who do support us at more than at $10 or more, I get to try and read your name at the end of the show. I think it's kind of fun. On next week's show, we will be back. Hopefully, Blair will be back broadcasting live from our Twitch, YouTube, and Facebook channels at 8 p.m. Pacific time-ish on Wednesday. If you want to listen to us as a podcast instead of live, look for This Week in Science wherever podcasts are found. If you enjoyed the show, please get your friends to subscribe too. Please. I think it would be wonderful, don't you? Yes. We love your feedback. Send me an email, right? If there's a topic you want us to cover, address, a suggestion for an interview, please let us know on one of our social media accounts. Like I said, send me an email. Put TWIS in the subject line, though, so your email doesn't get spam filtered into a Pineapple Express slamming into the California coastline during this particular El Nino event this winter. I would never find it in that downpour. We look forward to discussing science with you again next week. And if you have learned anything from the show, please remember, it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in 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 Science.